now to the new topic of momentum in gradient descent. So let us recap the equation of gradient descent. We said that the new value of the parameter, and we have used multiple conventions. We have used the convention beta tilde, I used to say for next value of the parameters, beta being a vector, is equal to beta, current value of beta, minus alpha times gradient of the loss with respect to beta, right? Implicit, that is, with respect to beta. This is the original equation that we did in ML-100. We are familiar with. Excuse me. When we deal with deep learning literature, you find that people use a whole variety of conventions. So most of the time we are talking of a weight, right? So you can say that in our notation, I've been using this notation that if you look at the weight vector, its next value, I'm using tilde for next, is equal to the value of the weight vector minus alpha times the gradient, obviously with respect to weight of the loss, right? Written out in specific terms, ij. Let's look at the specific address of that of the layer L. So suppose I have in the layer L layer, just the ith node, and then in the L-1 layer, there is a jth node. So the weight associated with this edge is Wijl. This is just to recap, right? So the next value of this is equal to a Wijl minus alpha, and then the gradient, when you do it, it becomes a partial derivative, of course, because you're being very specific, Wijl, right? This is laying it out in specific pieces. So far, so good, guys. Right. So this is the convention that I've been following everywhere in deep learning course, fundamentals course. I've replaced beta with this, and here also beta. Any particular beta I is equal to tilde is a beta I minus alpha dl d beta I in specific component wise, right? That is what it is. So far, so good, guys. This is, I hope, a recap. Furthermore, now for the purpose of to align with the convention given in this book, so I'll say to align with the which we are using for review. What are we doing? We are replacing W with theta. We are saying that this W vector, it goes to theta as a vector. It's assumed it's a vector. And my tilde goes to t+1. You're saying that in the t+1 iteration, right, the theta, now does he use subscript or superscript? I forget. Maybe t+1 is equal to, this is essentially in my language, W tilde, right, is the previous value of theta in the previous step minus eta, right? So this in my language would be, this part would be W, and this would be, what is this eta? And gradient of so let me just write it here. This book writes it as gradient, writes it as a G vector, G, and for some reason makes it into a superscript, right? So the convention is slightly inconsistent, but for whatever it is, this is what the book follows. So now, what is the eta in our language, guys? What is the eta in our language? What are we calling it?
Alpha.
Learning rate. Yeah, this used to be the learning rate, alpha. And what is this guy, this beast, this GT? What is this? This is basically our gradient with respect to theta t of the loss, isn't it? Like in our language, this is what it is, the gradient of this part. If you replace your W with theta. So far, are we together, guys? Is this anything looking mysterious? It's a little bit of jargon, nothing has changed. The intuition is the same. It's just that different people will use different notations. Why am I confusing you with new notation? I don't want to, but I'm just making you familiar with the notations of a book that we'll use for review. So far, so good? Are we together, guys? Okay. So we will start with this as a gradient descent equation. So
here the T refers to the iteration?
Tth iteration.
It's sort of like time.
Tth step, yeah, T. And that's how people think. That's a very good word you use. Think of it as time. Time moving in discrete jumps. Yeah. First step, second step, third step, fourth step of gradient descent. What is each step? One mini batch, right? When the data, one update to the parameter value is one step, right? So the Tth iteration, and think of T as time, if that helps you, right? So the gradient descent equation is, now, guys, if all of this is getting too theoretical, I promise you, this is our last pure theory thing. After that, we'll use all of this knowledge for practical architectures from next week. Huh? So according to this, it is theta t plus 1 is equal to, I'll just repeat it here, theta t minus eta gt, right? Obviously, this the vector is assumed, and I will just deliberately write it in our notation, just for whatever it's worth. This is equal to the previous iteration of this minus alpha gradient of the loss, right? These two are equivalent. This is the way to think about it. Equivalent, right? But different symbolic conventions. Now we realize that this is the basic gradient descent equation. When we do, we said that the learning rate shouldn't stay the same as you go from epoch to epoch. So suppose you decide to train the data for 100 epochs. What should you do? We saw in the loss function visualization, which I can bring back again. Let me do that. It should be sitting somewhere here. Let's go. Do you notice that? We'll again keep referring back to this picture. In the beginning, let us say that you are up here. What do you want to do? You want your learning rate to be small or big? Can you guys see my mouse?
Yes.
Okay. So in the beginning,
it can be bigger.
Yeah, you want it to be big. You want to take rather large leaps because you want to fall off these little crevices quickly.
Local minima.
Closer and closer to the minima, as the epochs evolve, you want to slow down. So at the beginning of each epoch, you need to decide what your learning rate should be for this entire epoch, right? And that is what we did when we did the learning rate scheduler. The learning rate scheduler, to recap, the learning rate schedule determines what learning rate learning rate you will consider for each epoch. And this is very important. You change the learning rate after going through an entire epoch of data. So it is course grade. You don't keep changing it in the middle of the epoch itself. You do that. And so this equation becomes your fundamental equation, t plus 1 got modified to t minus this part got replaced with the learning rate scheduler, right? Which is a function of, right? I will just mark it. It's a function of t and the current value of theta, theta t, and which epoch you are in, and so on and so forth. That times the gradient t. So we did not touch the gradient itself. We had all sorts of ways to do this. We had the cosine annealing. We had the exponential decay. We had the stepwise decay. And stepwise, yeah, well, let me just call it stepwise decay for better word. And then there is also one that is sensitive to the plateau of loss function. Now, this I didn't get time to cover, and I don't think I'll get time to cover today. So how about this? We make this a reading assignment for you guys, and we do it at some point in the lab. Kyle, did we create a lab using the plateau also?
No, just with the stepwise and exponential.
Just the stepwise and how about cosine?
Yeah, it is working.
So there, okay,
yeah.
good. But plateau is not there. See if we can add
No.
also. So guys, your assignment is
Okay.
the plateau rate scheduler, learning rate scheduler on your own. And if it looks confusing, then I'll cover it in one of the Sunday sessions. All right, guys. So now one thing is there, eta learning rate became this, but we did not play around with the gradient. Now we are going to play around with the gradient. We are saying that this equation, the next step is we are going to play around with theta t minus, and whatever your learning rate is, I don't care. Maybe you leave it as a constant eta. So for now, for the sake of this argument, to keep both of these things separate, I'll just keep it as eta. And this becomes some function of t, right? And theta t, of course, of theta and t, the current value and t. So we have replaced the gradient with a much more sophisticated version of the gradient. We are saying we won't literally use the gradient, but we'll use some function of the gradient, right? Now, why in the world would you do that? The reasoning is very much like what we talked about before. See, if you don't have a momentum, a velocity, what happens is, did you remember that we used to get, if you come down and you hit this point, any one of these local plateaus or local crevices, local minimas, you will get stuck there, right? Because if you try to move away from there, the gradient will point back at it, will take you back. Are you seeing that? So in other words, suppose you are in a situation like this, you are here, right? You are here. What is the gradient here? 0, isn't it? Gradient is 0. Would you agree? Or let me just say GT, but to use the convention notation of this, GT is 0 at this point, right? And so you have been coming down here, you're at this point. Your gradient is 0. So what will happen? Learning will stop. No matter what your learning rate is, your learning will stop here. Because whatever you multiply, whatever your eta is, you're multiplying it by 0, right? So the next value of the parameters would be the same as the previous value of the parameters. Would you agree? Guys, are you seeing this? It's an obvious statement I'm making.
Yes. Bounce out of local minima.
Yeah, one of the downsides of a remote class is I can't see your faces, so I can't see whether you're understanding or not. But yeah, let us assume that you are. So speak up, guys. If you don't understand, speak up. I'll assume that silence means you're understanding it. Now, what you want to do is you want to somehow have a modified gradient G, which will make you go past it. Something that will make you go past it, right? And go past it enough to jump beyond that, jump beyond the local, make you take a step to here, something like this. Are we together, guys? So you realize that the local gradient is not enough. What do you need? We can take the velocity or the momentum we have developed coming down. And what we do is we say G is, in some logical sense, momentum plus the gradient plus GT. How about that? Logically, if we use it that it is the sum of momentum and GT, then what will happen? We will move past this minima, local minima. Am I making sense, guys? Right? The same is true for the plateau. Suppose I have, you would just stop here, gradient is 0. But if you're on the roll, you will roll past this.
But when GT equal to 0, you multiply by 0, you always get 0. So how is momentum going to help you?
No, because your total G is the past momentum plus GT. You're saying when I do the gradient descent, I will use G, capital G, right? So even though this goes to 0, but because this is greater than 0, I will still move, I will still update my parameters. Are we agreeing, Manish? So let's say that by the time you reach this place, your momentum was 10, right? So what is your G? It will be 10 plus, and the actual gradient would be 0. And so your update step would be what? T plus 1 would be your previous value of T minus eta times G, which is equal to 10. Right? So you will still end up updating your parameters. Manish, you got that?
Okay, yeah.
That is the whole point. What you don't want to do is stop at every time the gradient vanishes. You don't want to stop. You want to have from somewhere, borrow from your history, from your recollection. You have to borrow a direction and say, I'll continue to go in that direction. And what is the preferred direction here? The preferred direction here is follow this curve, right? Continue moving this, or follow this. Don't stop here. Keep moving here. Right? So you don't just bring this G, you need to have an intelligent way of having some G, some momentum, some velocity. So that is why these approaches are called momentum-based methods. Right? So where is the momentum going to come from? The momentum can be like, we can take the simplest form of momentum. The couple of methods we'll talk about. One is the stochastic gradient descent, SGD, momentum. For historic reasons, it's called SGD momentum because this is stochastic. Remember stochastic gradient descent. The stochastic gradient descent used to be that you learn what is your batch size in stochastic gradient descent? One, right?
Yeah.
Mini batch size. So what would happen? It would zigzag its way to the minima. And then even when it reached the minima, it will keep zigzagging its way around it. We saw that. Yeah. So this momentum term was initially created, and it's really useful to fix stochastic gradient descent, but it doesn't apply only to stochastic gradient descent. It applies to mini batch gradient descent also. Right. So keep that in mind, that the name is a bit of a misnomer. So what do we do? What we do is we say that we create a definition. We say that we create a term called velocity or the momentum. Velocity, momentum. See, remember, if the mass of a particle is 1, what is the momentum is the same as velocity, right? So that's the way people write it. So Vt plus 1 is whatever it is whatever your previous velocity was multiplied by a fractional amount. This is anything between 0 and 1, right? Plus your learning rate times GT. So now look at this term. This is your, this is effectively your new G, T plus 1, right? What you're doing is you're saying take the G, take the learning rate, but add a little bit from the momentum from the past also to it. This is exactly what we did here, right? So you can take mu is equal to, for example, 0. Depends upon how much you want to consider momentum, how strongly you want to consider momentum. Now let me show you in very practical terms. Remember that, so look at this thing. We will do it visually. I will take this. We will do gradient descent, but as we do it, close this one, settings. This is the momentum, very high momentum. See, this is your degree of momentum, right? Think of this as your the mu here. Do you want it close to 0? So when your momentum is very low, like 0.01, what happens? Let's see. I will start here.
You will get stuck.
Ah, did you notice that we got stuck here, guys? Well, then it gets stuck at the next place. You never know whether it will ever reach the minima or not. It sort of is bouncing around and going somewhere else, right? So what is happening? If you look at it, if you look very carefully, it is got caught up in this local minima here. Do you see this, guys? And it's a pretty significant minima. And the next thing you know is it will get caught up in this minima. And this is a pretty deep minima, hard to get out of, right? So now I will start from the same place here. And what I will do is I will take a bigger momentum. Let's say momentum is, how much should we take? Let's say, I don't know, 50%, half the momentum, let's say. Now what happens? I'll start at the same place.
Is it generally between 0 and 1?
Yeah, 0 and 1, that mu. So now you notice this is a pretty big valley here. Do you see that this was pretty deep? Half. So you're taking the consideration of momentum. 50% is coming from the gradient, 50% is coming from the momentum. What happens? Doesn't help. Remember, I told you that you'll get stuck in this deeper valley. You're stuck in this big valley. That much momentum is not enough to get you out. Do you see this, guys? Just looking at this, you know that you really need a strong amount of momentum, right? So let's go and do that. Let's go and do that again. And this is what we are doing. We are learning by playing with it. Let's do this. Let's take a bigger momentum. We take a really big momentum, right? Right. And then what do? Let's see what we can do. We again go here and try clicking. This is really actually a hard direction because there's so many traps along the way. Right? And you realize something happened. What happened? Let's go and see what happened. The momentum caused it to bounce around quite a bit. Do you see that? It did get caught up in the local minima, but after a little while, the sheer momentum took it across. Where did the momentum come from? From falling down this very, very steep mountain, isn't it? And so that momentum carried it forward. It made it knock off very fast here, and then finally it came here. Look at this. So do you see the value of adding a momentum term to the gradient descent? Guys?
Oh, definitely.
This is it. This is the basic intuition. So the rest is just algebraic equation. So what we are saying is this is our new GT. So when we take the step t plus 1, it is equal to whatever the t value was there minus, this funny thing, which is a mu times v, the previous t, minus eta gt. So you're saying that add a little contribution of past velocity. right? And this pass velocity, so V2, you can keep doing this. Now you will realize that what it means is that the past gradients that it has encountered, if you look at Vt plus 2, you realize that this will become mu Vt plus 1 plus eta Gt plus 1. And now what was, if you look at this, you substitute the value here, it is mu times mu Vt plus eta Gt, right, plus eta Gt plus 1. So one of the effects you see that the prior 2 steps before momentum is getting mu squared. And this is getting, the learning rate is being again reduced by mu eta. So this is just algebraic ways to say that the momentum that you encountered many steps ago, the gradients that you encountered many steps ago, their influence is gradually fading. You are much more impacted by the gradients that you have been encountering in recent steps, right? That's yeah, go ahead, Albert.
So here you can see visualization of that problem. Right?
Yeah.
So if you have a low momentum and you just let it go and you don't reach the,
Yeah,
so how do you solve that problem? Right?
your accuracy won't be good. And so you will see, this is it in deep learning. The one of the biggest problem is, given the non-convex loss surface or the complicated loss surface, you should never trust your first run of the data. You should always try out different values of the hyperparameter. Right, so you have to do quite a few runs.
So you have to go all the way from 0 to 1 in the momentum you get one.
You have to play. So now that brings up a next question. Well, you know, it's computationally very expensive. Some of these learning things run for days. So you don't get the choice to keep on running with different hyperparameter values. So that brings us a very interesting question. How do you find the best value of momentum, the best, you know, all of these are hyperparameters of the model, right? How do you select those? And that brings us to the whole world of automated machine learning. And that automated machine learning is a big topic, big topic. Today is the most important topic because there are so many hyperparameters in this deep learning world, right? So suppose there are 10 hyperparameters, and for each hyperparameter, you take 10 possible values. Let's say momentum, the mu, you take 10 possible values, 0.1, 0.2, 0.3, 0.4, 0.5. But then you realize that you're multiplying by 9 other factors which have 10 values. So 10 to the power 10 is 10 trillion. And each time you train the model, suppose it takes you 1 hour to train the model, you don't have 10 trillion hours. Even if you were infinitely rich with infinitely huge amount of hardware and patience, your lifetime is not 10 trillion hours, right? So the fundamental question is that these models that take so long to train and have such high number of hyperparameters, how would you find the optimal hyperparameters? And the search for that hyperparameters is variously called optimal. So that is a problem. And you can't do it by gradient descent because there is no gradient there for hyperparameters. For parameters there is, but not for hyperparameters. So you get into this very fascinating. Did I talk about Bayesian today?
Yes.
Right? So it is
Yes.
the power of the Bayesian reasoning or Bayesian mathematics that comes in. And the process is Bayesian inference and Bayesian optimization. Those things kick in and they give you an elegant way, a very elegant way to quickly zone in and find the best combination of hyperparameters, right? In very few steps. And it's just marvelous to do that. Now, it is worth mentioning. Do you remember, guys, that when we did the basic machine learning course, ML-100, people often talked about grid search. But I told you that grid search is actually a terrible idea. At least at a very bare minimum, use randomized search, which is better, right, for hyperparameters. But now I'm saying that even that ultimately has a combinatorial explosion of possibilities when you have very high number of hyperparameters. So it doesn't work actually in practice for deep learning situations, deep neural networks. What works is this Bayesian optimization. Bayesian optimization is a core area of research. Somebody once told me that if you look at the total amount of money that the different companies are investing in this topic, the sum total is more than $1 billion just to make progress in this area of hyperparameter tuning and Bayesian optimization and so forth at this moment, right? So there's a huge investment. I don't know how true that statement is, but I do know qualitatively that there's a massive investment in figuring out the best hyperparameters and the Bayesian optimization problem. And this whole thing of learning hyperparameters. See, hyperparameter is not just the gradient, your learning rate or momentum and so forth, or the learning rate schedule. There's more than that. In a neural network, how many layers should you have in the neural network? That's a hyperparameter, isn't it? To solve a problem. How many nodes should be there in each layer? That is a hyperparameter. Which activation function you should use is a hyperparameter, isn't it? And now I just introduced one more. I'm saying that, well, the mu is your hyperparameter. Yeah. And so on and so forth. Even which momentum methods we should use, because now I'm going to introduce you to 2 more momentum methods. So that is a hyperparameter. And we can go on. And so how do you find the best hyperparameters? That gets interesting. And we'll do that as we continue the journey over the months and into the various courses. This topic of automated machine learning is so important and so absolutely hot today. It is not something we can do as an aside in one lecture. It is something we should talk about in depth properly in the course of 2-3 weeks in a subsequent course. So we won't do that. So this is it. Now, this is the SGD momentum method. It has a hyperparameter mu. What is its effect? The effect of this is quite interesting. Let us say that you take one particular parameter, right? Theta j, the jth parameter, right? Which in my language is wij of layer L, right? Suppose the value of this is continuously moving in this direction, right? It's pulling you forward. It's gradient, the gradient of loss with respect to theta. Sorry, let me put it this way. Like every time you take a theta j step, theta j t plus 1, right, is equal to theta j in this language of t minus this term, the step term, the gradient term. Gradient plus momentum term. What happens is that if all the time, let's say that it is increasing in value, right? What do you learn from that? During the learning process, it is moving every step, it's moving in the right direction, isn't it? If on the other hand, this thing was continuously going up, going down, going up, going down, going up, going down, going up, going down, what do you conclude from this?
You reach the minimum.
Your learning rate is too large.
You could, you have many things, but generally, basically, right, you don't want to take this, this zigzag too seriously, because averaged out, it is going nowhere, isn't it? This theta j is basically wiggling around and staying the same, right? And there are various causes, like you said, learning rate and this or that. But suppose other things, learning rate is fixed in an epoch. And as you do the steps, the hundreds of steps that you do, remember that the 2 for loops are epochs and mini batch step. Mini batch step. And remember, T refers to the step. For mini batch step, you do the learning step. The gradient descent step is the last thing here. Remember the 4 points, and gradient descent is right the last part. You take the step. You compute the forward pass, you compute the loss, you compute back propagate, and then you take the step. Right? So when you take the step and you notice that something is behaving like this, what do you want to do? Suppose you learn within this epoch, your learning rate is fixed, whatever the learning rate is, even if you're using a rate scheduler. But what you want to do is for this theta I, in which all the changes are in the one direction, you probably want to take bigger steps. But for this one, where it is just wiggling back and forth, you don't want to take much. You don't want to do this like a roller coaster ride. You want to more or less take small steps. You just maybe a little bit wiggle is okay. Keep it more or less the same for the jth parameter. Does that make sense, guys? Right. So one parameter continuously shifts forward. You want to pick up momentum in that direction and go faster. Another parameter is just wiggling around. Well, you don't need to pay too much attention to the wiggle. You want to just dampen it down, isn't it? And
Is it because we want to make it converge? Because it has already reached the minima and we just wanted to converge. Is that so?
for that one, yes, quite likely. For the jth parameter, if it is just wiggling around, it probably is just oscillating or around,
Right.
or is unstable, or has reached the minimum, or one of the many reasons. But you realize that something that just keeps doing that, what can you conclude? You might as well take the average value and sit there, right? You don't want to listen to the wiggles, the gradients too much for that thing. So in other words, how much you listen to the gradient, if it is proportional to the momentum. For the ith one, let's look at this. For the ith one, every time you're moving in the same direction. So what happens? All the gradients are nudging you to have higher and higher momentum, isn't it? Picking up velocity when you add the term. On the other hand, here what happens? All the gradients are canceling each other out. One gradient cancels the previous gradient, cancels the previous, that one cancels the previous one, that one cancels the previous one. So what does the momentum term be? Momentum will be approximately 0, isn't it? Would you agree, guys, that the momentum term, well, let me use the V term, velocity term will be basically 0 in this equation, right? And the only thing you're doing is you're looking, if your learning rate is sufficiently small, you're just listening to the gradient, up, down a little bit, up, down a little bit. You're wiggling around. But in this case, where this particular parameter, which is benefiting and going in steadily in the same direction, you're taking bigger and bigger steps because you have momentum there. For the same fixed learning rate, you're taking bigger steps. So the lesson to learn from this, and I would like to show it to you. There's a beautiful diagram in your book, which I would like to use. Now, let me bring up this application. What is it called? Cruise. CRU. Why am I not? Oh, not Kazur. CZUR. Strange name for a, yes, CZUR scanner. There it is. Bear with me, guys, for a moment. And I want to show this in a beautiful picture in your book. This is on page 173 of your book. And I would like to show this. New version, blah, blah, blah. We'll do that later. Scan. Oh, we are in, why are we scanning? Batch, color, visual, better. Okay, guys. So look at this thing. If all of your changes for one particular parameter, one particular weight, they are all, are you able to see my mouse, guys? Right. Look at this. Folks, are you able to see my screen?
Yes. And the wiggles.
All the
arrow
are steadily moving in the right direction. What do you want to do? You want to amplify the steps, right? On the other hand, if your gradient is, you notice that continuously oscillating. Yeah. So what do you do? It is very inconsistent. So what do? You just say, forget about it. We want to suppress these oscillations. We don't want to listen to it too much. Okay? That is the main point of a gradient-based method. And so what happens is when you let me clear this. When you actually apply momentum, where am I? How do I clear this? Yeah. So look at this. Here, without momentum, you notice that in the good situation also, we are taking small steps. In the bad situation also, we're just bouncing around. We don't want to bounce around. And here we don't want to bounce around, and here we want to take bigger steps. That is what momentum helps you do. What happens now is, now look at this. I'll zoom in a little bit more. Do you see that here you are, each step, I don't know if you can make out, each of the arrows are becoming longer. Each of the steps are becoming bigger, a little bit bigger. Yeah. And here it is, let it keep oscillating, but at the end of all of those oscillations, it just keeps moving back and forth and getting there, right? So complex oscillations, they do you no harm, basically, right? And this part I wanted to show you, it has a limitation though. When you use this gradient descent method, what happens is, see, you added this term and this term. You remember these two terms we were adding. Mu times the previous momentum plus eta, the learning rate, times the gradient, right? This is the equation that we wrote. Is it making sense, guys? We just now wrote this equation. Where is it?
Yeah.
Yeah, this is
in the book.
Yeah, here it is. So this is what we wrote. So now it has a problem. One problem that it has is that imagine that you're moving very fast here. Here, momentum tends to take over. Because you have a strong momentum, the gradient doesn't have that much influence. So here, where is the minima? If you're here, the minima is in this direction, isn't it? See, look at this blue arrow. From here, it is pointing in this direction, isn't it? Let me, I hope I can draw it here. Let me use a color that will be visible over that. Maybe this color will be visible. Right. So at this point, right, where is the minima pointing to? This is the big island of minima. So the gradient is pointing in this direction, right, which is this guy. Gradient is pointing in this direction. Which direction has momentum? Momentum is in, let me take yellow, right? Yellow, or maybe I'll take blue. The momentum is in this direction, isn't it, guys? You see, you have been coming along this line. So momentum is still along this direction, right? Your gradient is pointing in this direction. Momentum is along the blue direction. So the additive effect of these two will be, in which direction will you go? You will end up going in the direction marked here, namely you'll end up going here, because that is the end result of these two momentums, right? Well, this software is not terribly good, it's smudgy, but bear with me. Does that make sense, guys? If you look at the effect, the momentum vector overwhelms the gradient vector. Are you seeing that, guys? Yeah. Right.
It reminds me of the circus riders who ride in a cage, and they keep riding.
Oh yeah.
Yeah.
But they never
Driving
fall
in
down.
circles.
Yeah. Their momentum overrides the.
Yes.
They don't go crash on their heads.
Yes. So now, the problem with this is when you let the momentum take over and you have a very shallow or very steep, like, valley, right? If you think about it like this, let's go back to this picture. See, when it is, look at this. This is a fairly steep valley, right? Minima is here. So, and some of these other visualizations, they have even more steep. This is a pretty good, nice big minima, but in some cases, the valleys are very steep. So for example, let me find in this surface a rather steep valley. Oh yes, here it is. Look at this. Suppose this was the global minima. Suppose this is what it was. You realize that you could easily miss it on your journey home, right? You could go past it in some other direction, right? Without veering towards this, which is the point that this book is making, that if you don't pay attention, you'll go here, and the next time you'll go here. So you have literally blown past that very steep little valley there, right? So there is a trick you can use, which is actually a very popular form of momentum. What it does is, and the argument is pretty elegant. It says that don't take a step like this. Take the step in two forms, take a two-step process. First, what you do is you let the momentum take you somewhere and then compute the gradient from there. See here, at this point, let me say, right at this point itself, we are computing both the momentum and the gradient. Isn't it, guys?
Yes.
Right? Yeah. But suppose we did this. Suppose we did the opposite. What we did is, now pay attention to what I'm saying. Suppose here's the minima. Right, or suppose at this, you are here. And let me mark it in color, bigger, fatter. No, this is fat enough. Why is this not very bright white? Completely white. Okay, let's see. Suppose your momentum is carrying you. Suppose your momentum. Okay. Suppose your momentum has been carrying you here. So what will happen is, if you listen to the momentum term, it will take you here. Right? Now, imagine this surface. So you listen to the momentum. Let's say that the momentum is carrying you along this direction, right? So it takes you here, and you let this little intermediate step take place. You reach from X to X prime, this location, right? Or let me just say theta, because that's the convention your book uses, theta to theta T prime. Actually, this really makes it up with T's, and I'm trying to be consistent with it, which is a little bit of an inconsistent notation, but that's okay. You go here, and here you compute the gradient, and the gradient will now point which way? This way, isn't it? And then you take the gradient learning step here. So this becomes your T plus 1. So you go from theta T to theta T prime to the momentum. You're following the momentum for part 1. And from that location, wherever you end up with, now you take a gradient descent step at the gradient, right? Gradient T step. So this becomes your T plus 1, right? So what happens is that you will get a much stronger gradient if you veer off in the wrong direction, right? That is what this thing is saying. Now, let me bring this part forward. Yeah, I want to see both of them side by side. Okay, now look at this. Here, let me remove all of the markings and let me mark this to line with this line. Okay, guys, I am trying, this software is not the best. Line with, how do I line with, make it very small, okay. Let's see if this helps. I'll make those diagrams again, guys. So here, at this point, momentum was carrying it in this direction, right? Momentum. Gradient is taking you this, and you eventually end up going this way, as this picture shows. But in this, what you do is, let's say that the momentum, it is still taking you this way, right? But what happens? Look here carefully. You are in a much steeper gradient situation. At this point, do you notice that the gradient is much steeper? Right? Yes. I don't know if you can make out. It's a much steeper gradient. So what will happen is the gradient will push you much more strongly inwards. And so the end result of this two things will be this final motion, which we should give in some color, some lovely color. Which color should we choose? Let's say, I seem to be exhausting the colors. Let's try this. And so you would agree that these two lead to a movement in this direction. And this is nice. So you first took a step, followed the momentum, you went far off, Then you computed the gradient, which takes you steeply back in. And so your net motion is in this direction, vt plus 1. But you actually took 2 steps. And so you don't fly off the handle you're doing here. In the left one, you're just sort of flying off. But here, you have a much stronger pullback. And so you converge to your solution much faster. And that is why this form of finding the gradients this is a very popular, and for the longest time, it was the standard. And this is the Nesterov momentum method, right? And so this is, guys, this page is around 170. You must study. Nesterov is written like this, Nesterov and ROV. This used to be the most popular method for a very, very long time, and its variants. Well, state of the art keeps moving, and now we have many more methods. So the new family, or the king of the hill, is something called adaptive momentum, right? And adaptive momentum has more little detail. We will go into that. What I will do is, because we need to cover more territory, you got the main conceptual idea. Now think, people are doing optimization after optimization. So this book author says that they use Adam as the default because it's the state of the art. Well, the state of the art has moved even further. Now people use Adam W as keep making improvements, but conceptually is the same, right? I will discuss about Adam in perhaps an extra set. I would like to use the next hour to talk about normalization, a new topic called normalization. Are we done with momentum? We get the main idea of momentum, that when you do gradient descent, not only you go along the gradient, but you also consider the momentum from the past. That is the core lesson to learn. And when you do that, you don't get easily trapped into local minimas. You don't shallow minimas. You move forward in the right direction. So far, so good, guys. That's the main lesson.
Look, you're referring to the same yellow jacket book, or you're referring to another book?
This book is, for those of you who missed it, this is this book.
Oh.
It has just come out, guys. It got published a couple of weeks ago. It got published after we started the workshop, right? And so highly encourage you folks to get a copy of this book. Oh, by the way, Kate, did you look at the bulk discount thing for the whole class?
Oh, I need to make that call. It's the poll worker has been taking my time. I'll see if I can call during break tomorrow.
Sure, yeah. No, don't do that. You're busy with the poll, right? We can do it next week. We can certainly do it next week.
Okay, it's on my list.
Yeah, no hurry. So that is it, guys. If you're saying this whole course seems to be about gradient descent, right? In some sense, we have spent a lot of time on gradient descent for a reason. See, neural network surfaces, large surfaces, as you saw, are highly complicated, non-convex surfaces, isn't it? They don't look anything like my nice, beautiful convex bowl, right? With one single minima. Instead, they look like what they look like, namely, they look something like this. Oh boy, it is both fascinating, beautiful, extremely frustrating. So for many years, people said that neural networks are a hopeless cause. You cannot do learning using a non-convex non-convex loss surface. And there was a whole winter. Deep neural networks have gone through many winters. There is interest, then it dies off, then again it surges, some fundamental problem gets solved, it comes back with the surgeons, people start using it, and then again they get stuck and the whole field dies off, and then again there's a resurgence. So we are literally in the next resurgence of neural network theory. Right, the deep learning is, most of the breakthroughs have started since representation learning work of Geoffrey Hinton. So Geoffrey Hinton is one of those people in this field who's very, very influential. He's one person who stuck through all the winters and believed in neural networks when people were abandoning hope in neural networks. So one of the reasons people did, there are many reasons, but some of them were legitimate. We didn't know how to solve problems. Neural networks weren't getting us anywhere. because some of the core pieces we had not discovered, people had not discovered. So it wasn't quite working in as many situations that people would have. But it was never not working. It was always working very well for some situations. So one of the things people theorized was that because the loss landscape is so complicated and non-convex, therefore you can't really do neural networks. It's a hopeless cause. Well, people learn to all of these techniques that I taught you, the momentum, the simulated annealing, the learning rate, the cosines annealing, the learning rate scheduler. You realize in the next one, I'm going to teach you one word, the normalization and the regularization and all of those things. Each one of them, small as they have made a profound difference. They have made neural networks work, even though these ideas that you're being introduced to, these concepts, they look small or they look straightforward. Historically, they are of tremendous relevance. This is what has made this very complicated, made it possible for us to learn in this very complicated loss surface. So people now, the Jeffrey Hinton and people, they joke, they say that machine learning experts were suffering from something they call convexivitis. You know, the illness called conjunctivitis of the eyes, right? So they joke that people that you must have a convex loss surface. They suffer from convexivitis. They only can work with convex surfaces. But deep learning does just fine with highly non-convex surfaces. So guys, if you have been here with me, trust me, you understand more about neural networks than most people practicing in this field. There is a joke that Andrew Ng used to make long ago at Stanford. He would give a course in machine learning, and when people submitted the first homework and did it successfully, he would tell the grads, he would tell the Stanford students that congratulations, now you're machine learning experts. So they would all get surprised because they have just picked up basics, linear regression and so forth. And then he would give the second part of his statement. He would say, it is because most people who claim to be machine learning experts in Silicon Valley actually know less than that you know. Right? And in the same spirit, I can genuinely tell you guys, if you have followed me up to here, without exaggeration, I can tell you that your understanding is already deeper than most people in this field who have not bothered to understand this field deeply. They are all, code junkies. They'll pick up code, copy code from here, from there, pick up libraries and try to get the work done. And sometimes it works, sometimes it doesn't. But when you really understand the subject deeply, you have a mastery, you have much more confidence that you can solve any problem that this neural networks can solve. You'll get there in a short time. So that is a very important level of confidence to have. So we are going to end with the gradient descent thing now. We will talk now of a much simpler topic. And once again, I'll give you no more than a 5-minute break. We will now talk about normalization.